name's David Stevenson. I work for a company called Global Graphics Software, which is now part of the Hybrid Software Group. One of our sister companies is Meteor, that do printhead technology or printhead electronics. And I'm going to talk about a very specific issue that we have with driving industrial inkjet. So let me carry on. Right, yes. Intelligently estimate, optimize and tune. So let's talk about it. So we have a Global Graphics are the makers of the Harlequin RIP, and it's been built into a product called Smart DFE, which is specifically aimed at industrial inkjet. It supports industry standards for factory integration, such as OPC, but it has a particular architecture, which we'll talk about in a moment. But some of the challenges that we have are that the variable data is driving, and the advance of printhead technology means that the amount of data that we need to actually transfer to the printheads is getting ever bigger. We're going up to higher resolutions. The speed at which the substrate is being thrown out is increasing. The presses themselves are getting wider. We're having to deal with more inks, so extended gamut, and multi-level screening in order to screen that contone data into a raster that can actually be sent to the heads. So what we've identified is the thing that we refer to as the data rate barrier, which is to say that there is so much data that we need to transfer, that we have an architecture that looks something like this. So this is our Harlequin RIP technology here, and then we have our ScreenPro technology for actually doing the screening. The PDF comes in here, gets ripped, and what you'll notice is that there isn't any kind of intermediate storage. The idea with this architecture is that we can rip fast enough to actually generate the rasters and send them directly to the printheads. And there's the Meteor logo there. So the thing about this is that this bit is kind of deterministic. We know how long it would take to screen a particular size of raster. But this bit is kind of tricky because of that thing called PDF. So the thing about PDFs that we all know about is that they are wonderfully flexible. They can contain lots of different object types, images, fonts, etc., etc. We know all of this, color, etc. And also there is interaction between those objects in order to actually composite the page. So what we wanted to do was we wanted to find a way of trying to estimate how long it will take for a given job, a given PDF, to go through the RIP. And it turns out it's a really tricky problem. So the way that we've come up with this, well, there's actually two parts to it. One is the analysis. The other thing we want to be able to do is, if we have analysed the PDF, there may be opportunities also to optimise it in some way. So we've all used pre-flighting software, perhaps, that can downsample images. That's a simple way of making a job go faster through a RIP. But there are more subtle things that you can do as well in order to, without compromising the quality of the job, optimize it, make changes to the way that the PDF is constructed so that it will go through the RIP faster. Another example is actually to flatten transparency, but you've got to do that in a very special way, or a specific way, in order to not compromise quality or color integrity. So these are the things that we're doing. optimizing, sorry, the analysis. How do we do that? Well, or rather the estimation. So what we decided to do was use some other technology that the Global Graphics has called Mako, which is an SDK. And we use it to generate literally thousands. I think the training set, as it's called, amounts to about 2.1 gigabytes of PDFs that have specific combinations of objects, so images, text, vectors, and so on. And also built to interact in different ways. I've got a very simple example here of where we've got one image that is over another, so it's occluding the corner of this image. This image has an opacity set so that it will actually, there'll be some transparency, blending that needs to go on in this area. So we generate literally thousands of these PDFs, put them through the RIP and time how long those things take. What we end up with is with a huge data set. And the way that you can deal with a huge data set, if you want to use it to predict, is to apply a machine learning algorithm to it. And that's what we've done. So what you saw when that little animation was going was the process of training. So this is the process of taking that data, using the machine learning algorithm and teasing out the time it takes for given operations. And then we can apply novel data. We can take a PDF and put it through the same analyzer to look at all of the objects. But now we can assign a weight to those that says, if these two objects are going to be on the page, then it's going to take this long to do the compositing. And we end up then with an accurate analysis. The thing about it is, it is tricky. We have to be careful about the way that we do that analysis, because we have to do it on hardware that matches what our customers are going to be using. And the result is something that looks like this. So we can actually end up with timing results for each individual page. And what's interesting about this is we start to see patterns, particularly in VDP jobs, where the pages that are similar to one another actually have the same timing. And we can see those patterns become apparent when you do this kind of analysis. And we can also use that information to help us tune the RIP and to make changes to the way that the job is going to be processed to ensure that it goes through as quickly as possible. There's a couple of screen grabs here of the way that this kind of surfaces in the UI for our Smart DFE user interface. So the idea is that we have a little traffic light system here that will tell you whether or not the job is predicted to go through at the current settings in terms of line speed and so on. And then you can decide to mitigate that, maybe to optimize it, to improve the speed, and we can then analyze the optimized job. Or we can decide maybe to rip ahead, to do what you would normally do, which is just rip to disk and then print from that. And then we also produce a report which actually will give the operator information about the job and help him make decisions about what needs to be done about it. So that is how all of that kind of comes together in the user interface. And then finally, we have the idea of countermeasures. So I've already mentioned the fact that we can use this analysis to decide what we want to do with the job, and one of them may be to optimize it. So this is an example of optimization. So this is the analysis, the estimate of the job before it was optimized. So this one, oops, not that one. This chart here. This is exactly the same job estimated after it's been through the optimizer. So you can see it's you know, about, well, I think it says here 3 times as fast. So kind of a bit of offered a bit of a tangent compared to some of the other things we've been talking about. But it's a very interesting development, particularly interesting to me because I kind of own this from a product management point of view. Yeah, so anyway, if anybody wants to ask me or my colleague Jeremy about it, you can find us later in the break. So I think that's it from me. Cool.